This is problem 100 from chapter 12. We're going to go through this problem rather quickly, and if you feel like you want to give it a try on your own, I would encourage you to do that, and you can come back to check your work. The projectile is launched with a velocity of v0. Determine the range r, which is from where it is launched to where it lands, the maximum height h attained, and the time of flight. Express the results in terms of the angle theta and v0. The acceleration due to gravity is little g. So the important thing in this problem is that where the height at which the projectile lands is the same as the height from which it is launched. So we're going to start out looking for the range and delta t, which is the time of flight. So we are starting and ending at the same height. This distance from here to here is the range that we are looking for. We're launching the object at an angle of theta. Our vector here is v0 times delta t, and then pointing straight downwards, we have the vector 1/2 times the acceleration times delta t squared. We're going to take the hypotenuse and do that times cosine theta, which gives you r, and the hypotenuse times sine theta gives you 1/2 the acceleration times delta t squared, and the acceleration is equal to little g. We can take this equation and solve it for delta t. That gives us the time of flight, and then we can take that and plug it into our equation up here, and that gives us the range. And then, if you want to, you can use the trigonometric identity, which says 2 sine theta times cosine theta is equal to sine of 2 theta, to rewrite the range like this, which is useful because now you just have a sine instead of a sine and a cosine. This equation you might have seen in high school physics. This is called the range equation. It's not so very useful to us in this class because you can only use it when the object is being launched from the same height at which it lands. But there it is. Now we're going to look for h, which is the maximum height of the object. In order to do this, we should note that the maximum height is going to occur halfway during the time of flight, so the time at which it reaches the maximum height is half of the time of flight that we found here, and the position in the x direction then would be r over 2. So we're going to draw a new vector diagram where now we're multiplying v0 by half of delta t, and for our acceleration vector we're going to use delta t over 2, and the displacement vector, whoops, that's not the displacement vector. The displacement vector goes from here to here, and the x component is r over 2, and the y component is h. We really only need to look in the vertical direction, so you can take the hypotenuse, multiply it by sine of theta, and that's going to go from here to here, which is 1/2 the acceleration times delta t over 2 squared plus h. You can take this and solve for h, and then you're going to take the delta t, which we had up here, and you're going to plug it in to the equation that you have here, and then simplify it a little bit, and you're going to arrive at this result for h, and that concludes problem 100.